Welcome to Math with Professor V. This is the continuation for the video on factoring review for the calculus student, all part of the new video series, Algebra Review for the calculus student. So what we're going to do in this video is go over how to factor perfect square trinomials, differences of squares, sums and differences of cubes, and then apply these factoring techniques to find limits for your calculus class. So the first thing we're going to focus on are factoring perfect square trinomials. And previously, hopefully you've learned a pattern for squaring binomials. If not, I'll show it to you really quickly. So if you have a plus b quantity squared, you could sit there, write it out twice, and then FOIL. But it's helpful just to know that the pattern always works out to a squared plus 2ab plus b squared. And then similarly, if you have a minus b quantity squared, that multiplies out to a squared minus 2ab plus b squared. And this is helpful because when we encounter perfect square trinomials, if we recognize this pattern, then we can factor very easily. So we're just going to go backwards now. If you see a squared plus 2ab plus b squared, that's going to factor into a plus b quantity squared. And similarly, a squared minus 2ab plus b squared factors into a minus b quantity squared. Okay, let's work through some examples and I'll kind of talk you through the thought process. So factor the following. I know already they're all perfect square trinomials, so the pattern's going to apply. So if we have x squared minus 10x plus 25, that fits this pattern. You put the square root of the first term first in the parentheses, square root of the last term second in the parentheses, and then the sign of the middle term is what goes between them. So this is going to factor into square root of x is x. Square root of x squared is x. Technically absolute value of x, but we won't get into that right now. Square root of 25 is 5. Since there's a minus sign in front of the 10x, there's a minus there, and then this whole thing's squared. And then just to make sure it's a perfect square trinomial, you want to confirm that 2ab, so 2 times x times 5, really gives you the middle term, which it does. And then we're done. Okay, let's try another one. X squared plus 14x plus 49. So here I'm just going to put x, square root of 49, 7. Squared goes outside. This time this is positive, so I'm going to put a plus. And then you just want to double check that the pattern holds. So it's 2ab, 14x. 2 times x times 7 is 14x. Perfect. Here's another one where it's especially helpful to know this pattern. Because say you were in the wild factoring. In the wild meaning you don't already know it's a perfect square trinomial. You're just doing math and then this thing pops up, right? The first two, a and b, that I did, you could have factored them fine if you didn't know they were perfect square trinomials. But this one you might be like, holy smokes, what do I do? Well, Professor V taught me the AC method in the previous lesson. But if I were to sit there and go, okay, I need to find two numbers that multiply to whatever 16 times 49 is, and that add up to 56, I mean, that seems like cruel and unusual punishment. That's insane. And you're right, it is. So whenever I see a problem like this, I go, oh, maybe it's just a perfect square trinomial, because believe me, nobody hates you that much that they want you to have to sit there and work through something so nasty. So what you do is you just go, okay, square root of 16a squared, that would be 4a. Square root of 49, 7. Since this is positive, I'm going to put a plus. And then I just want to make sure, was it really a perfect square trinomial? Does the pattern hold? Is 2ab 56a. So 2 times 4a times 7, yep, it's 56a. So see how easily we were able to factor. This would have worked, but believe me, you don't want to do it that way. Okay, let's try another. M squared plus 2/3 m plus 1/9. Again, you kind of guess at first. Square root of 1/9 is 1/3. And then you double check and hope it worked out for the middle term. So 2 times m times 1/3. Yep, 2/3 m. We're good. Here's another one. I mean, this would just be sheer insanity to try to factor if you didn't recognize it was a perfect square trinomial, right? Could you imagine? 64 times 81 adds to negative. No, thank you. But then you go, oh, 64, yeah, that's a perfect square. So 8x, square root of 81, 9. This is negative, so I'm going to put a minus sign, and then we just got to check that the pattern fits. So 2 times 8x times 9, yep, 144x. Last example, F is dangerous. Yes, because you might say, oh, 36a squared, that's a perfect square. This is a perfect square. But always take the GCF out first. If you try to do it after, believe me, it's much more difficult. So first I can take out a 4 from everybody, yes. Then you have 9a squared plus 24ab plus 16b squared. Very good. So this is 4 times. And then you see, yes, this is still a perfect square trinomial. Square root of 9a squared, that's going to be 3a, plus square root of 16b squared is 4b. And then just let me be super safe. Is 2ab, 24ab. 2 times 3a times 4b. Yes, 24ab. Perfect. How do you feel? So like I said, when you're normally doing problems, no one's going to come and say, hey, this is a perfect square trinomial. But when you know they exist and you run into things to factor that look very intimidating, just remember that, because it may be much more simple to factor than you would have thought. Okay. Also, in previous lessons, we've learned a pattern for multiplying the sum and difference of two terms, conjugate pairs, and we're going to use this information in reverse to recognize and factor the difference of squares. So if you see a squared minus b squared, that's going to factor into a plus b times a minus b. And you can switch that around. You could write a minus b times a plus b. It doesn't make any difference, but that's how you factor a difference of squares. So let's apply that now. Practice some factoring. Y squared minus 9. That's going to factor into y plus 3 times y minus 3. Good. 4x squared minus 36. Take the GCF out first. So take the 4 out first. Then you have x squared minus 9. Then that's 4 times x plus 3, x minus 3. If you don't take the GCF out first, it doesn't come out nice, because then you have 2x minus 6, 2x plus 6. Then you have to factor a 2 out from each of them. So 2 times x plus 3, 2 times x minus 3, and then those 2's together give us the 4. So just take it out from the get-go, believe me. Okay, next one. Looks a little scarier, but don't be intimidated. 16a squared minus y squared over 49. So square root of 16a squared would be 4a. Square root of y squared over 49 would be y over 7. So you have that twice. Once with a plus, once with a minus. And that's it. What about x squared plus 4? That's not a difference of squares. That's a sum of squares. And a sum of squares is always prime. Sum of squares. It's not x plus 2 quantity squared, because that would be x squared plus 4x plus 4. Nor is it x minus 2 quantity squared. That would be x squared minus 4x plus 4. And x plus 2 times x minus 2 would be x squared minus 4. So see how a sum of squares is always prime over the real numbers. Yes. Okay, and then sometimes it takes multiple rounds of factoring. So I wanted to give you a little reminder. Always be sure to factor completely. Here we have 16k to the 4th minus 1. So already it's a difference of squares. No GCF that I could take out. So you factor into 4k squared plus 1 and 4k squared minus 1. But then always be on alert. This is, again, a difference of squares, so I can factor further. You leave the 4k squared plus 1 alone, and then this factors into 2k plus 1 and 2k minus 1. Good. What about x to the 4th minus 7x squared plus 12? Again, this factors into x squared. Think of two numbers that multiply to 12 and add to negative 7. So x squared minus 3 and x squared minus 4. But we're not done, because x squared minus 4 is a difference of squares, yes? I know, so we've got x squared minus 3 times x plus 2, x minus 2. Now it's factored completely. And then occasionally we also see patterns that use a difference of squares or perfect square trinomials a little bit differently. And I just wanted to show you some examples. For example, 49 minus a plus b squared, that's a difference of squares. You would have 7 minus a plus b times 7 plus a plus b. And then I could distribute this negative and write it as 7 minus a minus b. So that's a little unusual, but still works. And then here I want you to notice, when we went over factoring by grouping in the previous video, I said the majority of the time when there's 4 terms, you factor by grouping. This is the exception. A squared plus 2a plus 1 is a perfect square trinomial. This is a perfect square. So I'm not going to factor by grouping. It actually won't work. I'm going to rewrite this as a plus 1 quantity squared minus 9b is 3b squared, right? Can you see now how this is a difference of squares? So this ends up being a plus 1 plus 3b times a plus 1 minus 3b. And that's it. Good? These are just patterns that come up, and the more you know to look out for them, it'll make your life so much easier while factoring. Last pattern I want to go over are factoring sums and differences of cubes. Now we went over, you can factor a difference of squares. A sum of squares is primes, but that's not true for cubes. Both are factorable. So a difference of cubes, if you have a cubed minus b cubed, here's the pattern. It factors into a minus b times a squared plus ab plus b squared. So I'm going to give you like a little mnemonic to help you remember the signs. And you want to think of SOAP. SOAP. SOAP stands for same sign. Then you have the opposite sign. And then the last one's always positive. Let me show you what I mean. So this was a cubed minus b cubed. So this is the same as the original, minus. Then we have opposite. And then the last one's always positive. S-O-A-P. Now you just have to remember a squared, ab, b squared. No 2. A squared, ab, b squared. Okay? And then similarly, you can use SOAP for the sum of cubes. So then you're going to have same, opposite, always positive, and then it's always ab, a squared, ab, b squared. Same, opposite, always positive. Good? The nice thing is, once you've got this formula down and you know how to apply it, the majority of the time this is prime, this little trinomial here. So you don't have to worry about factoring further, usually. Okay, so here we go. Let's look at some examples. Factor x cubed minus 8. I'm going to go slowly in the beginning just in case you guys are getting used to it. So x cubed minus 8 is a difference of cubes. Here's the pattern. Let's identify a and b. So a is x and b is 2. If you want, what I like to do when I'm first going over this with students, set your parentheses up, put the signs in. So it's minus. So same, opposite, always positive. Then you have a, b, a squared, ab, don't write x, 2x, and then b squared. And that's it. Because x squared plus 2x plus 4 is prime. It's not too bad, huh? You just got to know the pattern. Okay, 27m cubed plus 125n cubed. So a is 3m. Just take the cube root to determine a. And then b, take the cube root, it would be 5n. So set your parentheses up first. Same, opposite, always positive. A, b. Be careful here. A squared is 9m squared. You have to square the 3 also. A times b is 15mn, and then b squared, 25n squared. Very good. Look at you guys. Got it? Ready for the Math Olympics? They don't have it. Okay. 8k cubed plus 1. So a is 2k B is 1. Let's set the parentheses up. Same, opposite, always positive. 2k, 1. Be careful. What's a squared? Oh, so good. 4k squared. AB, 2k, b squared, 1. Bravo. Bravo, you guys. D might be scaring you for a minute, but don't be scared. You might say there is no cube root for 2y cubed that comes out nice, nor is there one for 54. You're right. You got to factor out the GCF first. So take a 2 out, then this is y cubed minus 27z cubed. Now it's each are perfect cubes. So A is y and B is 3z. Excellent. So we're going to have 2 times, let me set it up, same, opposite, always positive, A, B, a squared is y squared, AB is 3, I'm going to put yz, let's go alphabetical order, that's usually the convention. And then b squared is 9z squared. Good, good, good. Look at us blazing through, factoring professionals. Last one, z to the 6th plus y to the 6th. So z squared cubed is z to the 6th. So that means A is z squared and B is y squared. Okay, that one might be hard to identify. And then from there, you should be good to go. So same, opposite, always positive. AB, so z squared, y squared. A squared, z squared squared is z to the 4th. AB, you could write z squared, y squared, or y squared, z squared. I said let's go alphabetical order, so let's do that. And then b squared would be y to the 4th. And we are done. Good? Okay, so now let's put it all together. We've pretty much gone over every factoring scenario possible. So let's find some limits that you're going to see in your calculus classes where you need to factor using these patterns. So evaluate each of the following limits. First one we have is the limit as t approaches 3 of t cubed minus 27 over t squared minus 9. So if you just try to plug in or substitute 3 for t right now, you get 0 over 0, which is an indeterminate form. But we notice we can factor both the numerator and denominator, so let's do that. Don't forget you got to write lim every step of the way. So limit as t approaches 3. T cubed minus 27 is a difference of cubes, right? So let's set it up. Same, opposite, always positive. A is t and B is 3. Very good. So this is going to be t minus 3, t squared, 3t, 9. How does the denominator factor? It's a difference of squares, right? So it factors into t minus 3 times t plus 3. Beautiful. Look at us. Now I can cancel out t minus 3. And then we have the limit as t approaches 3 of t squared plus 3t plus 9 over t plus 3. Can I use direct substitution now? You bet. This is 3 squared plus 9 over 3 plus 3, 6. So this is 27 over 6, which is 9/2. Fabulous. Okay, let's try another one. Limit as x approaches negative 5 of 2x squared plus 9x minus 5 over x squared minus 25. So if you try direct substitution, you get 0 over 0. 2x squared plus 9x minus 5. So you can factor that using the AC method that I showed in part 1 of this video, if you like it. I like just doing trial and error, so I'm going to walk you through that. 2x squared, that only happens by multiplying 2x and x. The only way I can get 5 is by multiplying 5 and 1. So now I just got to figure out, is the 1 here and the 5 here, or is the 5 here and the 1 here? Well, I got to get 9x for my middle term. So just imagine the 5 needs to be here, so it'll get multiplied by 2. It needs to be positive. There's my 10x, and then minus 1 times x is 9x. Beautiful. X squared minus 25, that's a difference of squares, so that's x minus 5 times x plus 5. Perfect, so these two factors cancel. And then now I have the limit as x approaches negative 5 of 2x minus 1 over x minus 5. If I use direct substitution, 2 times negative 5, that's negative 10 minus 1 over negative 5 minus 5, that's negative 10. So this is negative 11 over negative 10, which is positive 11 over 10. Good? I just got two more, don't worry. We've factored plenty. I just want to show you how to work it in with your calculus. Why don't you pause the video, try this one on your own. Limit as u approaches negative 1 of u plus 1 over u cubed plus 1. Give it a go. What did you get? Did you get 1/3? Okay, let's try it together. So this is the limit. U approaches negative 1, u plus 1 over, denominator is a sum of cubes, so same, opposite, always positive, u, 1, u squared, u, and 1. Good? So u plus 1 cancels. I still have a 1 in the numerator, right? Even when everything cancels out. So limit u approaches negative 1, 1 over u squared minus u plus 1, 1 over, now negative 1 squared is going to be positive 1, minus negative 1, that's positive 1, plus 1, so this is 1/3. Good? Okay, last one, I've put this on an exam before. X to the 4th minus 16 over x minus 2. A lot of them get it wrong, and it made me sad, so I thought, we need to review factoring, even in calculus. X to the 4th minus 16, that's a difference of squares, so it's going to factor into x squared plus 4 and x squared minus 4, and then we have x minus 2 down here. Now remember, sum of squares is prime. Difference of squares can factor further. So this is the limit as x approaches 2. You leave x squared plus 4 alone. And then x squared minus 4 is x plus 2 times x minus 2. And we still have x minus 2 down here waiting patiently to be canceled out right now. Whew. And then we can find this limit. So limit x approaches 2, no denominator, it's just x squared plus 4 times x plus 2. If I substitute in 2, that's 4 plus 4, so 8 times 4, this is 32. Okay, very good. So that concludes factoring perfect square trinomials, differences of squares, and sums and differences of cubes. In the next video, I'm going to go over just a general strategy for factoring, because obviously you're not going to know when you're out in the wild, like I like to say, solving problems. It's not going to always be perfect square trinomials or always be a sum of cubes. You need to look out for certain cues to know, ooh, what technique should I use? So I'll walk you through that process, and then we'll try some more limits, and then we're going to move on to reviewing other algebra topics. The next thing that we definitely need to go over is finding domains of functions, because I know students have a hard time with that. So I got you. I've been teaching for long enough, and I know what things my calculus students have forgotten over the years to really cater and tailor this video lecture series to help you guys who are embarking on your calculus journey. All right, that's it. So don't forget to give the video a thumbs up, subscribe if you haven't already, and then follow me on Instagram and TikTok, Math with Professor V. I'll be back sooner than later. Bye, guys.